Hey, this is Mike here for CPSC 330 doing a screencast for Lecture 12, which we didn't actually do during Lecture 12. We didn't talk about feature selection, and instead we just did more midterm reviews. So here's what we didn't do. I'm going to stick to the housing data set from last week for this, so I'm just going to load that up and run the same pre-processing code that we had from last week, so nothing really to look at here as far as I know. Okay, cool. So the first thing we're going to talk about is feature correlations. I guess this was a note to myself, but we did do that a little bit in lecture 10, so that's all good. And so the idea is to look at correlations between various features with each other and also with the target. And so that's going to give us kind of our initial understanding of what a particular feature might be doing. Now keep in mind that regular correlation is a linear correlation, so when you just call it like a core function, which means that it doesn't capture more complicated relationships like when you increase x, the target goes up and then down and that kind of thing. It's only looking for a general trend correlation, and so it's not exactly a measure of, if the correlation is 0, doesn't mean the feature is useless. It might mean that it goes up and then back down, and it's actually a very useful feature if you pass it into a random forest or something like that. But it's still a good start to look at. So here you have the sale price, which is the target here, and what you can see is I'm going to zoom out just for this part, and then I'll zoom back in later. Just a lot of features. Maybe I'm going to lower this down to not 20 features. Just feels like too big of a plot. Okay. So sale price and then all the features. And so this one on the diagonal with the strong blue is saying things are very correlated with themselves. Well, 100% correlated. That's not interesting. But you can see other things here, like this one right here. This 0.79 right here says that sale price. So we have all the rows and the columns are the same. The first row is sale price, the first column is sale price. We have all pairs of features here, except I'm not taking all the features because there's too many. I'm just taking the sale price and 14 other ones. So this 0.79 means there's a pretty high correlation between sale price and overall quality. And since that number is positive, it's kind of like a linear regression coefficient type thing. It's saying that as overall quality goes up, sale price tends to go up. So this is already kind of telling you some features that might be important or useful if you look at this first column here. And so this, let's see, year built seems to be have a pretty high correlation. Some things seem to have a pretty low correlation, like overall condition. I'm not sure how that actually, what that is compared to overall quality, but we can immediately start to get an idea of what features might have a strong linear relationship, at least. Again, not necessarily all types of relationships with the target. And then we can also look at the rest of it. What about the relationships between the features and each other? So for example, this dark blue box here says that first floor square feet and what is that, total basement square feet are very correlated. And so that's the type of thing where you might wonder, well, do I really need both of these features if they're really similar to each other? And sometimes it's good to have both because you squeeze out a little bit of extra information by having both. But in terms of feature selection, we're asking ourselves not only the idea of what we're talking about today's feature selection, basically what features can we throw away? And there might be things that are just not very predictive, like maybe this one has a very low correlation with the target, but there also might be features that are just kind of not that useful in light of other features being there, because it's very similar to something else or something like that. However, this is a very primitive kind of at a glance picture, but definitely not the recommended way of doing feature selection. There's so many problems here. For example, as I mentioned, there's relationships other than linear relationships. There's relationships that are mediated by other features. So maybe if you could look at the combination of two features, that will tell you something about sale price, and we can't get that here because we're looking at one feature at a time. We're only looking at linear, and we're not looking at like a particular model. Like if we're using random forests, well, what features are relevant for random forests is going to be very different than this. So this is like a useful at a glance, and if you see like a 1 somewhere, like two features are exactly identical, it would be good to notice that, because then you really might want to consider taking one out, or a -1 for that matter, meaning they're the exact opposite of each other. So this is not a recommended way of going about feature selection, but it's a nice kind of glance at what's going on, and I think Pandas Profiler produces a similar plot. So yeah, I think we talked about most of this stuff. And we talked about this stuff. Okay, so let's move into the next section. What is feature selection? So feature selection is finding the features that are important for predicting Y and maybe getting rid of the ones that aren't. And so it's very related to looking at feature importances, but it's more than just looking. It's actually changing the model by throwing away features. And so why might we want to do this? Why would we throw something away? The more the merrier, right? Well, there's a few motivations for this. One could be data collection. So maybe it's very expensive or laborious to collect all this information, and you're planning to collect way more data in the future, and so you want to know from the data you have so far what's actually useful, and if something's useless, you would love to not collect it in the future because it's expensive. Computation could be another reason. So the fewer columns of X you have, just the less number crunching there is to do. So everything should be faster, fit, predict, your whole prototyping loop. The fundamental trade-off. So we'll talk plenty more about that today, but having useless features can cause overfitting. And in the homework, there's an optional question where you added a column of random noise, and you saw that it helped the training score, and it actually got a relatively high feature importance. But that was all just overfitting. And so a useless feature isn't maybe as bad as random noise, but it could be almost as bad. And so we would like to throw those away because our model can find patterns in those features that aren't actually there, and we might want to throw them away. Okay, so how do we do feature selection? One way is domain knowledge. You might have expertise and just know, hey, this thing can't possibly be relevant in predicting that thing. There's just, I know from my expertise, like, well, I'm trying to think with the house price data set. I don't know, maybe like the day of the week that the house was built. Like, did they finish building it and file their permits with the city on a Monday 100 years ago or on a Wednesday 100 years ago? Like, that's just, if that was a feature, you would just know, get rid of that feature, because there's just no way it could be useful for, I think, for predicting the price in 2020. And then what we're really going to talk about today is importance-based feature elimination. And so basically, building on feature importances, which we talked about last week, we're going to look at those feature importances and basically throw away the ones that have low feature importance. That's kind of the punchline. But it's a bit fancier, but that's the punchline. Last year I talked about lasso, which is kind of like another linear regression like ridge. But I took it out because I think what we're going to talk about today is more general. It's not just for linear regression, and it's going to get the job done. But if you're interested, you can read about lasso or get to the notes from last year's version of the course, which are also available in the same GitHub repo. Okay. So, feature selection, importance-based feature elimination, that's the main thing we're going to talk about today. So we already talked about feature importances, and now we're going to use those to throw away features, and here's how it's going to work. Well, in the first way we're going to do this, we're going to decide in advance how many features we want to select. So we say we want 100 features to be kept and throw away the rest, or we want to throw away 10 features or something, and we'll automatically pick K later today. So then we're going to assign feature importances by doing that, fitting our model and looking at the feature importances, which will either be coef from a linear regression or a logistic regression, in which case we'll look at the absolute value of that to get an importance, or the actual feature importances coming out of scikit-learn. We'll remove the least important feature, and then we'll just fit a new model after that feature has been removed, and we'll keep doing that. And critically, this is not the same as just fitting the model once, looking at the feature importances and saying, I'm just going to throw away the bottom half. Because the thing is, once you throw away features, that changes the model and therefore changes the importances of all the remaining features. And so if you just threw them away, if you just threw away the bottom half versus you threw away one, refit, recomputed the importance, threw away another, refit, you're going to get different features. Actually, this would be a great exercise in class that I don't have prepared, but I think that would be cool. Let's add a to-do. Okay. Yes, so, and again, the reason for that is the features, it's all like the model uses all the features and they all influence each other. And especially in the more complicated models, the feature importances could easily change every time we take away a feature. So in scikit-learn, we're going to use RFE, which I believe stands for Recursive Feature Elimination. Documentation. Sounds good. So how many features, all that kind of stuff. Okay. So you can take a look at the documentation. Yeah, so I've been making a list of GitHub issues here in scikit-learn. I guess I'm not going to click on all of them or go through all of them, but long story short is that this scikit-learn is not yet ready for prime time in scikit-learn with pipelines or transform target regressor. The problem is if you try to pass in a pipeline to RFE, it'll try to ask the pipeline, hey pipeline, what's your coef? Hey pipeline, what's your feature importances? And in scikit-learn, it doesn't know for the pipeline to get the feature importances of the model in the pipeline. And yeah, I guess there could be good reasons for that, in that like the features coming in aren't even the features going into the model. It's probably a mess. But anyways, that is not implemented to the best of my knowledge. And likewise for transform target regressor, I don't think it has a feature importance. So if you try to use these RFE things with these, well, when I tried, I got errors, and according to the GitHub issues, that seems to be where we're at. So I'm going to be logging these myself instead of using transform target regressor, and I'm going to be encoding these things myself, meaning I'm going to use the already pre-processed data that looks like this, that is already scaled and one hot encoded and ordinal encoded and all that. And I'm not going to use a pipeline. And that means I am going to violate the golden rule here a little bit, in that the cross-validation is going to do splitting here after the pre-processing. And that's not the greatest, but it's hopefully not that bad. And we always have our test set at the end to give us a not messed up score to kind of see how we're doing at the end. So that's that. Taking the log myself, transforming before I pass it in here, violating the golden rule. I could avoid this by not doing cross-validation and just doing regular train and validation, and then just training my pre-processing on the train and then transforming on both, and then I wouldn't be violating the golden rule, but I didn't bother doing that here. Okay, so what do we got here? We have, I don't know, 86.86 r squared on our log transform data. And on the test set, we have, well, the test set we have something higher. This data set, again, is too small to really trust these scores. This is like 90 plus or minus 5% probably, because it's just, oops, such a small data set, really tiny. Okay, so here's what we're going to do. Well, actually, first, what I would like to do, and annoyingly, I don't seem to have it prepared. So here's the coefficients, but, oh boy, let's see if I can do this off the top of my head. Come sure you've all seen this error before and been upset about it, so maybe you can watch me struggle now as revenge. Why is this happening exactly? Oh, I see. Right. Okay. Don't do this to me, please. No. Okay, we made it. Right. Okay. Thank you for your patience. Hope you enjoyed that. So what I can do is I can also take the absolute value of the coefficients, because that's really our importance. If it's really positive and big or negative and big, those are both important features. And so what we see here is our unimportant features at the bottom. But again, we're not going to throw away all 5 of these at once. We're only going to throw away the least important one, which is, was it sold in September or not? We're going to throw that one away, delete that column, and then refit and recompute the feature importances. So that's what this code is about to do, this RFE code here. And so we make an RFE, we pass in our linear regression, we tell it how, so this says we want to keep 30 features in total. We fit it on the data set. So this is basically fitting the model, getting the feature importance, throwing away a feature, fitting the model, getting the feature importance, throwing away a feature, all the way until there's only 30 features. And now this RFE, just like grid search CV and all that, acts like its own scikit-learn thing where you can call predict with RFE, you can call score with RFE. And I think what we really want to pay attention to here is that are these train and test scores. And so what we found here is that, well, in this case, let me get the train score as well. So we had a 90 and a 90 basically, and then we went, so both of these got worse. So what this is showing here is that we're actually underfitting. We threw away too many features. And that makes sense. We only kept 30 out of 292, and now we just don't have enough to go on, so we're underfitting. Both of these scores went down. Which brings the question, how can we choose this number of features to select kind of maybe automatically? And that'll be coming up next. Stay tuned for that. But I want to show you this as well. So RFE.support tells you which columns were selected. So out of the 30, these are the ones that got selected. And now this would be the perfect time to take this feature importances or coef df. This would be the perfect time to say, give me the first 30 that's sorted. Right, here's the top 30. Beautiful. So here's the top 30. Contrast with the top 30 by the original importances. And what you're seeing here was this claim that I made up here with the to-do. So I actually did this. I could take that away. I'm showing that using recursive feature elimination, meaning eliminating features one at a time, will give you different results than if you just immediately threw away everything except the top 30 right from the beginning. And what we did here is considered better practice because the feature importances, as I mentioned, are different every time you throw away a feature. So the top 30 are different, and even the ordering is different. So this one decided overall cond was useful was second place, but originally it was only fourth place. But apparently, when we threw away all those other things, it changed from second place to fourth place. And again, our level of trust in this is going to depend on the size of the data set and a bunch of other factors. But if we went through these very carefully, I'm sure we could find something that was in here and not in there, and vice versa. I mean, if we were really serious about this, we could. Okay, so here's all the features that were selected in the RFE, but wouldn't have been selected if we had just taken the top 30 according to COEF from the original model. So that's cool. And here's the ranking according to the RFE. So all the ones are things that actually got selected, I believe, and then the rest are like the ordering of in what order did they get thrown away. Okay, so that's that. I'm going to do the exact same thing with the random forest, and all I'm really trying to show here is that here RFE and scikit-learn will automatically use the feature importances instead of the COEF because that's what is available here. So get a train score, get a test score. Now we see some overfitting, 89 to 82. We say I only want 100 features. Now it's taking a while because it's fitting the random forest, 192 times, going from 292 columns down to 100 columns. So we got to wait for that, and I think that's why I use these more modest hyperparameters, so it wouldn't take too long. So what do we have here? Okay, well, we have a minuscule improvement in test error. Not really within error bars, so it's hard to say that's actually an improvement. And I think what would be another good to do here is to plot train and test error, or really train and valid error versus number of features selected. Because what I want to get across here is that we have all these complexity hyperparameters like C for logistic regression or N estimators for random forest, max depth for random forest. All these hyperparameters controlling complexity. In a way, this is just another hyperparameter controlling complexity. The more features we keep, the more complex our pipeline is, and the fewer features we keep, the less complex. And all the usual fundamental trade-off stuff kicks in. More complex, better train score, more overfitting, more complex, better train score, less complex, potentially underfitting. And so it's different because it's doing something different. It's throwing away columns. But at the end of the day, we can just think about it as controlling complexity. The difference is there's some other motivations to do this other than just getting the best score, like changing the hyperparameter. Okay, I don't actually care what the hyperparameter C is, so just give me the one that gets the best score. Here, it might help me get a better score, and there's those other motivations like the ones we talked about earlier, like computational savings potentially in terms of predict, or data collection, or maybe I just want to look at what features were selected, or I want to tell someone about that. So it kind of plays this dual role. It could just help reduce overfitting, and maybe there's other reasons as well. Okay, what about categorical features? Yeah, so that actually, we had that before. So these are the selected columns. These are the removed columns. That'll be easier to read. Selected columns, removed columns, and what I want to say is for these one-hot encoded variables, because it doesn't take in the pipeline, it takes in the encoded data. The thing coming into RFE, this X-train encoded, is already the thing with the one-hot encoding and everything. So when it removes a column, that refers to this existence of columns post-transformation, post-preprocessing, post-one-hot encoding. So you might be removing things like foundation slab, but keeping other foundation-related features. It might not take away all the columns pertaining to a particular categorical variable. And so I don't know if you can spot better than me, like is there something fence related up here? It's a bit hard to spot with so many. But anyway, there's nothing preventing it from. I mean, for its point of view, they're just columns. It doesn't know that these 10 columns came from a categorical variable with 10 values. So, well, here's an example. Like, it's keeping months sold October and December, and it's throwing away all the other months sold. So now you're like, if you do things this way, if it's sold in October or December, you're going to have a 1 there in those columns, and anything else you're just going to have a 0. Which is also a little weird because of the handle unknown. Like, it kind of makes anything other than October and December like the same as an unknown category, which is a little weird. But yeah, there are kind of like more proper ways to remove an entire categorical variable, but we're not going to go into them here. So yeah, there's this is also being talked about in scikit-learn development. Okay, yeah, I feel like I should ask for questions, but of course there's no one here. So the next thing we need to talk about is how do we choose the number of features to select? And that was a hyperparameter above, if you recall, RFE, number of features to select, right here. So since this is supposed to be a complexity hyperparameter, if we're just doing this for the sake of maximizing cross-validation score, there's this RFECV, which basically automatically picks that value for you based on cross-validation score. And the idea is, as you remove features, the training score will always get worse because you want all the features you can possibly fit to get the best training score generally, but some of them might be overfitting. And so it's going to basically keep throwing away features. Every time it does that, the training score will get better every time. But the cross-validation score will perhaps get better at the beginning, but then start getting worse. And that's kind of now it's starting to underfit. I've taken away too many features. And so then it just stops and says, oh, I'm not going to take away any more features. So that's RFECV. It's kind of like I very briefly mentioned, like Ridge CV is like a ridge that automatically tunes alpha. So RFECV is like that. It's an RFE that automatically tunes the number of features to select. And the syntax is the exact same. The only difference in the syntax is you don't provide the number of features, and you can, if you want, provide the number of folds, but the default should be 5. So we can run this, and we don't really know how long it's going to take to run because we don't know how many features it's going to decide. Okay, here we go. So it decided to select 60 features out of 292 because apparently that's what got it the best cross-validation score. So that's kind of cool. And yeah, I talked about that already, so I don't need to talk about that again. So that's RFE, that's RFECV. Now let's talk about some warnings. So yeah, whether a feature is relevant or not is a really hard question, and so we're just approaching it empirically. We're basically saying, well, if I take it away, does the cross-validation score get better or worse? And that so our notion of feature, like whether we're going to keep it, depends on which model. So using linear regression will select different features than using Ridge, and I should have than using random forest, and I should have showed that above. That it whatever model you put in is going to maybe select totally different features. So again, you can't say like these are the features if it depends on so many things like what model, what hyperparameter is pre-processing, all these kinds of things. So don't take it as, these are the features that matter in this problem. Don't overgeneralize again to the real world too much. And yeah, another important thing to note is as you remove some features, other features could become important. So it actually could go two ways. Imagine only the combination of two features were interesting. Like if the house is big and has good heating, then it's great. But it needs to have both, because if it's only big and it has bad heating, you're going to freeze, right? So in that case, both heating and big could be important, but then once you throw away one of them, the other one could actually become unimportant. That's not a very good example, because it's not that they become unimportant. Maybe. Anyway, you can imagine that kind of thing, but it could also be the other way around. that these two features are almost identical, so one of them seems unimportant, but then when you throw away the other one that's similar to it, now that one becomes important. So as you throw away a feature, what I'm trying to say is as you throw away a feature, other features that were important could become unimportant, and that were unimportant could become important. So it's not too obvious to know exactly what's going to happen to the feature importance every time you remove a feature. Yeah, don't interpret any kind of causality. Don't be overconfident. We don't really know how the world works. We're just humble supervised learners trying to predict why and get a good score, and that's it. Okay. Yeah, this is sort of a thing about drop first. It's optional. We don't really need to go into it, but basically, since we're dropping columns after the one hot encoding, then we're like dropping the columns corresponding to a different to a particular category of a categorical variable. And so if you use drop first, that like already dropped one, but it's supposed to be arbitrary, but then you start dropping more, it gets all kind of messed up. But we don't care about that really, because this year I'm just saying don't use drop first, and so we're all good. I think that is all I had to say about feature selection. Hope you enjoyed watching. See you later.